Today we are here with Dr. Jetse Visser from the University Medical Center Utrecht in the Netherlands, and he is here to tell us about his most recent publication. The article is titled Reinforcement of Hydrogels Using Three-Dimensionally Printed Microfibers, which was published in Nature Communications. First of all, congratulations on your findings, Dr. Visser, and thank you for accepting our invitation for the discussion of your findings. Can you please start by telling us about the 3D printed microfibers and how they affect hydrogels?
Sure. Thank you. So we started off by printing the microfibers, and that's a pretty new technique, and the technique is called melt electrospinning writing. And this is basically heating a polymer, which is biodegradable. It's called PCl, or polycaprolactone, and then extruding it through a pretty fine needle, and there's an electrical field in between, so the fiber gets retracted from the needle, and then you have very thin fibers of 20 micrometers, and through a 3D printing setup you can build constructs that consist of all these microfibers. And then we want to reinforce hydrogels with these fibers because hydrogels are pretty soft. You can imagine your gelatin pudding, you can compress it a lot, and if you want to place such a hydrogel in the body, because we do so for regenerative medicine purposes, because we can mix cells in a hydrogel, for example, that grow a new tissue. This is a pretty new field in medicine, but still the hydrogel is pretty soft. Especially imagine when you put such a gel in your knee joint. If you want to focus on cartilage repair, you want to have it stronger because it will immediately get squashed when the patient starts walking. So we combined these fibers with the gels, and the most remarkable finding we did was that the gels get reinforced to a pretty large extent with these also very small fibers. So the fibers are soft, the gels are soft, but when you combine them, we saw their stiffness increased up till 54-fold. So that was a pretty remarkable finding.
And why did you choose PCl instead of any other material for the fibers?
We chose PCl because it's the most widely available and most diverse polymer to use in engineering, and PCl is available in medical grade, and we always focus on approaches that are easily translatable to the clinics. So we chose for PCl, and the degradation rate of PCl within the human body is within 2 years.
Okay, and I was looking at the structure of the mesh or the network, and I saw that they're like squares because you go from 0 to 90 degrees. And
Sure.
My question is, why did you decide on making them like squares instead of maybe a more natural, unorganized mesh of fibers?
So this is work I did in Australia, and I moved for a few months from the Netherlands to Australia. And when I was in the plane, I thought, okay, indeed, I need to mimic the collagen architecture, like all these arches, and that's probably optimal for the mechanical reinforcement of the hydrogels. However, also this melt electrospinning technique is only out there for a few years, and we're still limited in what we can do regarding architectures. We can make more than squares. We can make circles or other degrees patterns, but these arches are still not possible. So this could be regarded as the first setup of squares. So we're now working on new architectures. So you're right, it's a point of attention.
And have you thought of also making these hydrogels appropriate for different types of tissue, not only to mimic cartilage?
Sure, because we found when you change the spacing in between the fibers, you change the stiffness of the hydrogel. So in this manuscript, we focused on cartilage tissue because it's pretty challenging regarding its stiffness and also elasticity, and we managed to sort of approach both of them. But you can imagine liver tissue, for example. It's it can be softer, it's less biomechanically challenging, so you may even need to insert less fibers.
Okay, and what difficulties did you encounter during this project?
The first difficulty is having the melt electrospinning writing setup foolproof so that it always makes these nice squares. My background is medicine, so I'm an MD, and I'm not an expert in engineering, although I did a lot of engineering in the last few years in the biomedical field. So engineers helped me in that. From then on, it went pretty prosperous, I have to say.
And what future studies do you and your partners have in mind for the 3D microfibers?
That will for sure be different architectures, because ideally you would more mimic the native, for example, collagen structures of the tissues. These squares have proven there to provide a high stiffness to the gel, but may limit the horizontal migration of cells. So therefore, we also want to have more porosity in the horizontal plane, and we want to improve the resistancy of these reinforced gels to also shear loads, because now these manuscripts only focused on compressive loads, but we're not sure what they will do on shear loads. So we'll be basically the architecture of the fibers, but also move towards application of these reinforced gels for example, in cartilage repair, what we're currently working on, because we work in an academic medical center.
And have you thought about testing these hydrogels with stem cells to know what type of differentiation they may cause?
Sure, we didn't do that yet. We chose for chondrocytes here, but indeed, stem cells may be differentiated towards a certain lineage only based on their mechanical environment, and these microfibers, hydrogels, could be a mechanical stimulus to that, but that needs to be investigated indeed.
And finally, what future applications do you see for these 3D fibers in relation to the medical industry?
As PCL is a medical grade material, and as a few hydrogels can be available in medical grade too, I think it's a combination of biomaterials that can be readily quickly translated to the clinics, and that first focus will probably be in cartilage repair, because cartilage repair is relatively straightforward regarding the architecture and the thickness of the tissue, and it's not that large, so to say, and it probably starts there, and from then on we can move towards the regeneration or replacement of larger tissues, because there will be these microfibers. We're also working on combining them with other 3D printing techniques so we can build larger constructs.
Okay, well, thank you very much for your time. Once again, this is Dr. Jetse Visser from the University Medical Center Utrecht in the Netherlands, and his manuscript, which is titled Reinforcement of Hydrogels Using Three-Dimensionally Printed Microfibers, is available in Nature Communications. Thank you very much.
Thank you.